Well, thank you, Madam Chairman, and good morning. I've travelled across 13 time zones to get here, so I'm still a little bit on the bleary side, I guess. But hopefully I won't fall asleep if you don't fall asleep, okay? But I believe snoring is infectious, so please. Anyway, I'd just like to acknowledge some of my ASU collaborators, Hugh Barnaby, Yago Gonzalez Velo, Wenno Chen, Jennifer Taggart, Arsha Patadi, and Mehmet Balaban for basically doing all the hard work and allowing me to take all of the credit. Thank you very much. Oh, I did make a subtle change in the title, by the way. I put silica rather than SiO2 because, frankly, it's a little more descriptive of what we're doing. I'll come back to that in a little while. This is the outline of the talk. This is basically what the shape of the talk looks like, and I'm not going to spend a lot of time in each of these topics. I'll just give you a little kind of taster of each of these as we go through. Starting off with the need for new technologies. Now, of course, we've seen a lot already in this meeting of why we need new technologies. And, you know, looking at the trajectory that the device market, the electronics market has been through in recent years, you know, we see something that looks like this, where, you know, in the 80s, we began to get our PCs with our 20 megabit hard drives. I was astonished at that, 20 megabits, good grief. 2000s, of course, that led us to our awesome cell phones and the likes. In the 10s, you know, we saw an increase in mobility and ultra mobility, and obviously that's led us to where we are today, and in the foreseeable next 5 years or so, where we're really talking about the age of autonomy in electronics. And by autonomy, of course, what we're really talking about are, you know, Internet of Things, machine to machine, wearables, you know, that kind of stuff. So, who cares? Well, if you look at the just machine to machine and Internet of Things value chain, we're talking about some reasonably large numbers, as it turns out. You know, we're talking about billions of dollars. Even just in the kind of hardware side, we're talking about chipsets and, you know, and modules and the likes. Next year, worldwide in IoT, even though these things are by nature very inexpensive on a average selling price per part, we're still talking about several $1 billion worth. But I think more significantly, if you look at the kind of force multiplier effects of these technologies, you know, you look at this Cisco study here. I mean, various people have come up with various figures, but they're all big. They're all in excess of $10 trillion when you look at the knock-on effect of all these new technologies, these machine-to-machine Internet of Things, ultra-mobile. And you know, you just look at what it does to various aspects of our lives, and you can see why it results in such large figures. I mean, 14.4 trillion. It takes me about, 3 years to make that much money. It's ridiculous, you know, it really is a large sum. Okay, I exaggerated just slightly there. So what do we need technology-wise to meet these vast upcoming markets? Well, I mean, clearly one of the things that Professor DeMicheli pointed out this morning was we need incredibly low energy capability in these devices, low voltage, very, very low currents, and certainly picojoule or lower, you know, switching energies. Energy efficient computing, you know, in the form of neuromorphic systems and the likes. You know, there's various approaches to that people have been pioneering, and we'll have some talks on that during this workshop. Ultra mobility and I guess what you would also call inconspicuousness. When, you know, in the Internet of Things we have sensors and modules and the likes embedded in just about everything. We want very, very small form factor, and because they're sprinkled all over the place, we want extremely low cost. So we're talking about high density, compact design, not a lot of silicon used in the making of these things. Thin, not stacked modules, but heterogeneously integrated modules that may even be, chips, I should say, that may even be flexible for certain applications. And of course, you know, cheap and expensive also goes with simple integration with mature process technologies. You don't want to have to reinvent your CMOS to get these things to work, that's for sure. I put in radiation tolerance here, not just because we've recently received tons of money to look at radiation tolerance, but there is a need for radiation tolerance in devices, especially when you start talking about medical devices. Gamma sterilization of medical devices and the likes has been a bit of a problem for electronics, as you might guess. It tends to make it go kind of batty. Wearables, and of course mil-aero applications where all of these things could be exposed to either accidental or deliberate amounts of radiation. And then there's the whole security thing. I mean, this is a scary thing. We recently heard of distributed denial of service attacks that were initiated through the Internet of Things, which just, to me, I don't know whether to laugh or cry at that. Just the thought of my thermostat, going after some of the biggest companies in the US maliciously is just hilarious to me. Anyway, so let's talk about what we're up to. This idea of this cation memory that we like. It's a resistive memory. We called it 20 whatever years ago programmable metallization cell because essentially that's what it does. But there have been various other names that have been proffered for it. The one that the industry has taken up is conductive bridging random access memory. Thank you, Thomas, and his ex-colleagues at Qimonda there. There's also electrochemical metallization cells and stuff like that, but we still call it PMC as a kind of technology base. And the idea behind it is we have a solid electrolyte layer and an ion-conducting layer. It has ions that are either put in during processing or as part of a forming process. As far as what that layer can be, I mean, it can be just about anything that conducts ions, anything that's just obliging to ions moving through it. And as Ilya Valov pointed out in a paper we co-wrote, gosh, the materials can be insulators, they can be mixed conductors, or they can be classic ion electrolytes. Just about anything will do as long as an ion can move through it. The electrodes are, in our particular case, in these cation memories, we saw a great talk from the gentleman from HP earlier on talking about oxide-based, anion-based devices. We were cation. And in that case, we do need some form of oxidizable electrode that can supply ions into the reaction environment, and an inert electrode that basically just provides electrons for the reduction of those ions. And those electrodes can be typically on the oxidizable side, silver or copper, and on the inert side, it can be anything that basically can conduct but not react electrochemically with the system. So tungsten, platinum, that kind of stuff works fine there. As far as operation goes, we get oxidation and reduction at either terminal there. That results in an ion current. And the reduction of the ions actually in this environment, reaction environment, creates a conducting filament of some sort that bridges the gap, hence the conducting bridging moniker there that allows the device to switch from high resistance state to a low resistance state. And this little micrograph here, cryo-TEM micrograph, shows an actual filament between two electrodes. These are kind of elusive, as you might guess, to try and find it. You really need a large memory array program. It's a checkerboard, and then section lots and lots and lots of these things till you accidentally find a filament, or what looks like a filament, and then you declare victory. As was pointed out earlier, of course, it's much better to do it in operando rather than trying to do it afterwards, but we try our best. Reversing the bias in these devices basically oxidizes the filament. It goes away and then replates back from whence it came, so the device returns to, hopefully, its original state. Now, the interesting thing about these devices is that, like a lot of these resistive memory devices, the on-state resistance is actually a function of how thick the filament is, as you might guess, and just from simple, R equals rho L upon A kind of calculations. So the more charge you pump in there, the more ions you reduce, the thicker, the wider the filament, or indeed the more filaments that you grow in parallel, the lower the overall resistance. And you get this inverse linear relationship between on-state resistance and the programming current. It looks something like this, just showing you for a variety of materials. It holds for just about all the materials we use in these devices, with a typical on range in the order of a few K to a few tens of kiloohms typically as our normal operating range. And over these ranges, we can actually split it up into multiple resistance levels that can be used subsequently to represent different logic states. From the off state is 0, 0 through various intermediate states to the lowest resistance state to represent 1, 1. And we've succeeded in demonstrating that, as have various other folks in actual integrated circuits that use obviously programmable current sources and current comparators to detect the various currents flowing through these and decode those as multi-bit states. I should say that we do tend to draw the filament when we're explaining the technology as a conical structure that basically starts on the cathode in the lower electrode there and then grows up. And as it does so, it kind of fattens out at the first point that it grew at, and so you get more of a kind of cone forming. But I should say that any electrodeposition process requires, of course, a supply of ions. And if you have a material that is basically it's a low diffusivity material as far as the ions are concerned, and the metal is concerned, you can actually reach a situation where there are a lot more ions available for the reaction near the top electrode than near the bottom electrode, and it kind of inverts what you see with the filament. And there are some examples of that being shown in the literature. My favorite is Attilio Belmonte's work showing how these hourglass-shaped filaments form in very thin layers of aluminum oxide, where you have a lot of copper, for example, available for electrodeposition near the copper top electrode, coupled with a lot of electrons available for the reduction near the bottom electrode. And you kind of get an hourglass-shaped filament, which he has managed to image rather nicely there. Okay, so let's get to the main topic of this talk. Copper silicon dioxide or copper silica devices. Why am I interested in these over the myriad of other materials that are available? Well, a lot of the materials we really like in these devices, and by really like I mean that have high ion mobilities and switch fast and do all sorts of cool things, the guys in the fabs don't like them. Okay? Now, I come, despite my incredible youthful appearance, I actually come from many, many decades of working with fabs and have people tell me what I can't do. I'm sure the more mature of us will appreciate those comments. And you mentioned, say, something like a silver-doped chalcogenide glass, and after the fab manager stops laughing, then he tells you why you can't use it. So, there are some compatibility issues with the really good ion-conducting materials. Copper and silica, copper and SiO2, of course, are ubiquitous these days in back-end line. A lot of processes, foundry processes use them. So if you can make a switching device, a resistive memory device, based on that type of technology, it has more acceptability than a lot of the other stuff that's out there. I mean, okay, yeah, we are embracing more and more exotic, quote-unquote, materials in fabs, but you see where I'm going here. I mean, it's just a simple add to an existing CMOS process, and this just shows you one of our copper silicon dioxide device wafers. And we are busy at the moment porting this to a foundry to make actual product, just due to its simplicity, basically adding it to a logic process. So what do these things look like? Well, very, very simple. Just that kind of sandwich that I showed you before. Copper top electrode, a silica, porous silica, I should say, switching layer, and then, a conducting, whatever, tungsten, say, bottom electrode. We can deposit that oxide by PVD, or I'll show you in a second, CVD. We can pre-dope it using basically just thermal diffusion of the copper into the oxide, which takes several hundred degrees C, typically 500 odd degrees C, which a lot of people aren't 100% happy with in back-end line, but it is one way of pre-doping the oxides, which is actually, in essence, what it does is it allows you to reduce the forming voltage that you have to use in order to get these things to switch in the first place. So, it kind of makes the subsequent program of these things a lot simpler as we go along. But it does, the penalty is you're using a high temperature in the back end of line. The key thing is, though, it has to be fluffy. It has to be a low-density oxide, typically in the order of 15–20% less dense than a typical thermal oxide, and that allows it to switch very, very well. So you have to adjust your deposition parameters to achieve that. Here's just some of the performance-related graphs that can generally show you the kind of things that we see. For example, can we see that one here? Oh, no, we can't. But the blue curve there is the forming curve, showing the necessary forming sequence for getting the kind of nascent filament to to ultimately be switched. The red curve there is a normal switching on state curve, off state curve transitioning to on, and the other one towards the left is the on state. The plot in the middle there basically shows our retention at 85 degrees for these things. It's pretty solid, and then some cycling there showing the on and off state. So these things do actually work. I mean, surprisingly enough, even given their simplicity. The other option, I should say, for processing, and one that frankly the fabs prefer, is CVD. And it's an inherently low temperature process, using plasma CVD, say a remote plasma CVD or just regular plasma CVD process. We can put these oxides down at 200 centigrade, and there's no need to anneal. They're thin enough, typically 5 to 10 nanometers or thereabouts, so we get the copper in there without having to do a thermal anneal. And we can, again, adjust the deposition parameters so that we get that fluffiness of the oxide, that porosity that we need to get it to switch nicely. And these guys work pretty well. The off states aren't nearly as high as in the PVD ones, but they do switch rather nicely, and they're, as I say, they're nice for processing. Now, as far as the actual operation of these things are concerned, there's a lot of arguments about, well, what exactly is happening? How are these things switching? Do they switch, similarly to the chalcogenide-based devices, or what's going on? And one probe that we can use, of course, to see what's going on inside these things is impedance spectroscopy. It's a wonderful, wonderful tool for oh my goodness, I begin to sound like Donald Trump. It's a wonderful tool. It's the best tool in the universe here. It's wonderful, wonderful, great. No better. It is a good tool, though, for exploring the kind of electrical structure of things. And in this case, you look at the cold hole plots, and you see that the structure of these devices is actually not homogeneous. Typically, we've got in essence something that has a low resistance on top of a region as a higher resistance, and you end up switching the higher resistance, and you can see this as a kind of dual RC type of structure here. So you're really in these devices, and we can see this by impedance spectroscopy modulating that high resistance region, which is actually kind of cool. And it explains as well why these things can be quite fast, even when you have relatively thick oxides involved, 100 nanometers or thereabouts. On state, no big surprise there. It is metallic. It is a copper filament, and you can see that again by an impedance spectroscopy. When you get to the few k ohm on-state resistance, above there in the intermediate range, we have a number of interesting things going on at the moment. Nick Onofrio out of Hong Kong has done some very nice work in modeling these intermediate on states in these copper silicon dioxide devices, and you can see these tenuous copper filaments being responsible for the higher resistance on states. Now, one of the things we've always liked about being able to form a copper filament is that in making one of the electrodes, say N plus silicon, you can get a really nice Schottky diode out of it. I mean, who cares if you want a Schottky diode or not? Well, in creating a Schottky diode between that copper metal filament and, say, a lower N plus silicon electrode, you can get a kind of built-in isolation element, a built-in selector element. Now, these selector elements, I wasn't going to go into this in great detail just because of the time restrictions here, but the idea of having a selector means that you can have a complete crossbar structure where all of the devices are essentially connected together without a transistor having to be used as a selector. And having a diode built in allows you to isolate each of these devices from one another during programming and reading without having sneak paths through the other on-state devices. In other words, basically the diode provides a high resistance blocking of any sneak path currents through on-state devices. And being able to create that diode as part of the device itself is very, very useful. And we were able to do that just literally by growing a copper filament on top of the N plus silicon, showing here in the green and red curves for two different doping levels in the silicon. Basically, it's a Zener diode. Now, of course, because this is a bipolar device, it requires negative voltage to switch the thing off. It's important that that diode was Zener-like and had a negative breakdown, and indeed, in the highly doped case, the highly doped silicon case, we did get that negative breakdown allowing us to switch these devices off. In the likelihood case, we don't get the breakdown as you might expect, and the current, the reverse current is blocked. So, I mean, good for one-time programming things, but not for reprogrammability. And just in passing, I should say that these devices, you look at the right plot there, these devices are capable of being programmed at absurdly low currents, which could be useful, again, looking forward to ultra-low energy devices. In this case, Christina Schindler was able to get like 10 picoamp programming current. I mean, it probably took a week to program, but it was a pretty low current. Mentioned radiation tolerance, and I'll blast through this fairly quickly. As I say, we're very interested in radiation, in part because of medical devices, and in part because, again, the DoD in the US are very interested in these for space systems. And we chose 7.1 megarads, dose into SiO2, frankly because it was way above the lifetime sterilization dose for gamma sterilization in medical devices, way above there. And we can see that the devices behave very well throughout that type of radiation. And looking at performance, resistance, the ability to program to different resistance states, and the sort of general off-state and on-state behavior of the devices, there's very little change even after 7.1. In fact, we've taken them up to 10 megarads gamma in these, and we got pretty much the same results, which is very impressive. These things are hard to kill. There's been mention of low-energy computing, and of course, one of the ideas behind this, and there'll be way more on this during this meeting, one of the aspects of RRAM is to use, of course, resistive memories in place of a synapse. Now, of course, the whole idea of a synaptic element is the ability to change its weight, its strength, based on learning. The more you stimulate it, the stronger the connection gets. The less you stimulate it, or a negative that you destimulate it, you end up getting a weaker connection. And of course, the idea is that we should be able to use resistive elements in that context. It's the same kind of thing. The more you stimulate them, the stronger the connection gets, and you can erase them just as easily. So we looked at copper silica as a synapse, and we're actually quite surprised at how good the results were, looking at stimulating it with positive pulses and destimulating it with negative pulses, cutting to the chase here. One of the things that we saw is some relatively, and I say relatively linear and relatively symmetric, what we call potentiation and depression in these things. Now, what's significant about that is most systems, most resistive systems, when you're training them, they do not have particularly linear training ability. You tend to get curves that do this kind of thing, where they go up steeply and then they flatten off. In our copper silica elements, the potentiation depression was a fairly linear event, and just as delightfully, the symmetry that we got in the potentiation depression was also rather good over several cycles. And we're quite heartened by that, because this is something that our synaptic people, if you like, the neuromorphic people, really want to see, is this linearity and this symmetry. And we're getting there. We're happy that we're getting there quite well. As a final topic here, mentioned security for the IoT. We've got big problems there. There's no question about that. And one way that's believed that will help us is by using the same kind of security that we use for a lot of transmission of data over the internet, and that's to use challenge response pairs, which of course are very common in secure communications. And the idea is, you have a lock and a key, and you have to be able to, when you challenge the lock with a particular key, it has to respond appropriately and briefly. So in order to create these challenge response pairs, you have to have something that has natural entropy associated with it. Now, those of you who have worked in resistive memory will doubtless realize that one of the greatest criticisms was that these devices had a stochastic nature that would make it impossible for them to be used in any sensible memory application. Well, we got around that like we get around everything by basically brute forcing it. And every device in the world is stochastic nowadays. Every transistor is stochastic. Every flash device is stochastic. So, I mean, you get around it algorithmically and by, thresholding things and the like. In this case, we actually embraced the stochasticity, and we use these things to generate physical unclonable, or as physical unclonable functions, I should say. Now, this has been done in Flash. This is not a new thing, but the really cool thing about using resistive memory is very, very low voltage. So it really resists side channel attacks like differential power analysis and the likes, where you look at what the power rails are doing and you can extract what the chip is thinking by doing this. So what we did was we used these, again, copper silica arrays. And in this case, we actually used crossbar arrays because we didn't have to program the devices. Or if we programmed them, we could erase them afterwards and then just go through and look at each device in turn to generate our challenge response pairs. And the idea is, because you get a Gaussian distribution of, say, a parameter like the set voltage, you can use what set voltage you get as a 1 or a 0. In our case, we used 1, 0, or an intermediate state, which again the cybersecurity guys find very, very useful. It's way over my head, I'll be honest with you, but I'm happy to provide the devices. And we've got actually have a product that's being designed at the moment based on that we hope to fab in the aforementioned foundry. Okay, to conclude, the way ahead. Predicting the future is always very, very, very dangerous, to say the least. But one thing we can say is the reality of the present is there are devices in the marketplace based on these technologies. So-called CB-RAM, as made by Adesto. They've done some really nice stuff with that, using an aluminum oxide-based switching layer, and they get some great characteristics. Sony and Micron got together and built some fairly dense 1T, 1R type structures, so one transistor, one resistor cells. 16 gig was their test chip and got some impressive results out of those. And then we've heard a lot about these 3D cross-point things. And there's a lot of kind of head scratching, and it's a phase change. No, it's not a phase change. It's a phase change on steroids. No, it's not. And regardless of what it is, we do know from Micron that they have a couple of different generations of these 3D crosspoints coming down the pike. I know for sure one of them is ionic, which is really interesting. It'll be interesting to see what happens when that thing comes out. So, final thoughts. So we've got new technologies, new materials, ionic memory. It looks promising. I like our copper silica devices because they're cheap and cheerful. Seem to work fairly well. Might work in neuromorphics. We're excited about the cybersecurity side of things. I think a lot of the growth in any resistive memory is going to be driven by, frankly, the untethered devices, Internet of Things, machine-to-machine type stuff. But you never know. Could be some interesting things in the high-density memory too. Thank you.